Hey ladies and gentlemen, here's the video where I go over stuff about circular motion and universal gravitation. Here are some of the topics that I'm going to talk about. And here we start with circular velocity. So this is basically the speed of velocity going around a circle. How fast are we going around the circle? And we start with this idea that the distance around a circle is the same as its circumference. So let's say you have a circular path right there. Oh, that's an ugly circle. Okay, close enough. Okay, so the circumference is defined as 2 pi r. Okay, now velocity is the same as distance over time. So our distance is the same as circumference. So this velocity we can get is 2 pi r over time. Now this capital T versus lowercase t, there's a difference between them. This one is all about the total time interval, and this capital T is time for one revolution. Okay. And this velocity vector is tangential to the circle. So tangent, meaning it touches the circle once. So let's say we're going clockwise. So I'm drawing this arrow to represent we're going clockwise in the circle. That means you go in the normal clockwise fashion. And let's say our object is at this point right here. What is the velocity vector? Okay, so it's tangent. That means an object traveling in a circle, when it reaches that point, its velocity vector will be directed that way. Okay, like that. Now, in the event we have another circle, this time going counterclockwise, going the opposite direction, at the same point, this velocity vector will be just pointing in the opposite direction, leaving the circle that way. So again, it doesn't follow the circular path. It doesn't. It leaves the circle in a straight line fashion. So if you're swinging something around and you release it at that point, it's going to leave the circle in that straight line fashion like that. And then we have something called centripetal acceleration. And we start with this idea that the speed, which is the magnitude of a velocity, can remain constant. So you could stay at a constant 10 meters per second going around in a circle. But velocity includes both magnitude and direction. So while you're staying constant 10 meters per second around a circle, that velocity is always changing because you're changing your direction. You're never going in a straight line in a circle. And because of this always changing velocity, you're going to have a centripetal acceleration. And the word centripetal here means towards the center. So that's derived from Latin. Towards the center. So it always exists in a circle. So if I had to draw a circle here, and if you're at this point, then your centripetal acceleration is pointed towards the center of the circle, AC. Okay, wherever you are in the circle, if you're here, and you're there, it's always towards the center. Like that. Likewise, we have centripetal force. Because of Newton's second law, where a net force causes an acceleration, the fact that we have an acceleration means we have a net force. And that net force is called centripetal force. Okay? So just like centripetal acceleration, the centripetal force is also directed towards the center. So all of these vector arrows directed towards the center, they all represent centripetal force F of C. And then now it's important to look at this equation right here. Fc, the centripetal force, is equal to mass times the centripetal acceleration. Looking back, this is also in the reference table, centripetal acceleration is also equal to v squared over r, so the velocity squared over the radius r. You can combine both of these equations here to get this expanded form. So we know that AC here is equal to this. We could plug this in over here, and we should get this following form, which might be more useful than MAC in some cases. So this is the expanded form of the centripetal force equation. It's not on the reference table, but you could derive it from the other two. So we're going to look at this for our next two bullet points right here. So mass and velocity, m and v, are directly related to the centripetal force. If you notice, they're both in the numerator. So if both of these go up, so does the centripetal force. Okay, so if both of these go up, so does the centripetal force. Okay. Radius, on the other hand, because it's in the denominator, it's inversely related. So if you increase that radius, you make it longer, then the centripetal force, on the other hand, will decrease. And that's because it's in the denominator, it's inversely related. Now, there are going to be a few questions that would ask you some relationship analysis here. And there are two methods we talked about in class, dummy variables and graphing. So some of you have already come to ask me, is like, when do we know when to use this? How do we know when to use these methods? So dummy variables, you resort to that for specific numerical relationship analysis. So if you're looking in terms of like, if they give you numbers, if they say specifically what happens to this if you double that. So that means you're going to be working with numbers specifically. Whereas graphing is best used to see general relationship trends. So if they're just talking about increase, decrease, remain the same, it might be best to use the graphing method. Okay, it's just to get a look at the picture to help you describe if one is directly related or inversely related. Or the best shortcut is to just look at the equation, you know. But, you know, sometimes these other methods might work. So let's start with the graphing example. What is the relationship between centripetal force and each of the following quantities? So we're going to use graphing to analyze the relationships between mass, radius, and velocity. I know I've already mentioned them in the previous two slides about centripetal force, but it's still helpful to like practice these techniques so that we're able to use them in future units, because these things are going to pop up again and again and again. So we start with our general equation here, Fc equals mv squared over r. Let's start with mass. What is the relationship between mass and centripetal force? So we change this into a graphing equation. So our standalone force is y. We're changing mass to x. And the key thing here is to look where x is. Now, because it's in the numerator with no exponent, let's recall this is a linear relationship. Y equals mx plus b. Okay, so we could see that they both go up together at a constant rate. If mass goes up, so does the force, and it's the same rate together. Next, we have radius. We already said it's inverse, but let's see why. And that's because it's in the denominator. I want you to pay attention how it's in the denominator, without an exponent. So the inverse graph looks just like that. So notice how you're going to have a very short radius here. And as you increase the radius over the x-axis, look how the force decreases. So with a short radius, you have such a high force right here. But as you increase that radius, the force decreases. So it's inverse. And then we have velocity. This one's slightly different. So y equals mx squared over r. So pay attention again to where x is. It's in the numerator and it has an exponent. So x squared, think about the quadratic. Okay, quadratic relationship. So it goes whoop, exponentially. They go up together, but it's not at the same constant rate that linear has. It goes up quadratically in an exponential squared rate. So especially the further you increase that speed, there's a dramatic increase for the force. So that's how you use graphing technique to analyze relationships. Now here we go with dummy variables. So this is where you plug in numbers. You plug in your own numbers. Ideally, you probably want to use 1 instead because it's such an easy number to deal with. And so we're looking to see how the centripetal force changes when you double each of the following quantities. So let's say we start out originally, our original values for each of these three scenarios, they're all equal to 1. So we're looking for how these are affected. So what happens when all of these are equal to 1? So it's still equal to 1. Now, let's start with mass. What happens when mass is equal to 2, but everything else stays as 1? Okay, so 2 kilograms times 1 meters per second, and we square that over 1 meter. 2 times 1 squared over 1, that's still 2. So here, if you double the mass, you double the force. Radius will now be 2, but you keep everything else equal to 1. Okay, so 1 kilogram, 1 meter per second, squared over 2 meters. So now it's 1/2 of a newton. So notice there, we already talked about how radius has an inverse relationship with force. So when you increase the force, you double it, it halves the force, it decreases. So it's 1/2 as times, great, 1/2, great. And now finally velocity. This goes back to being 1, this is also 1, but now velocity is doubled. Okay, just plug and chug there. So now it's 4 newtons. Notice there, when you double it, it quadruples the force. It's quadratic. Alright, so dummy variables is used to look for specific numerical relationships. So doubling a variable will cause so-and-so to increase or decrease by this specific factor. That's what you're using dummy variables for, to look for the specific factor. And then finally, we're going to talk about Newton's law of universal gravitation. Shows how two masses set a distance apart can exert a force of attraction. So this is shown by this equation. F of g, big G, is equal to big G, m1, m2 over r squared. So we got two masses, m1, m2, over the set distance, r. Sometimes it stands for radius of a planet. And all of these values, sometimes you're dealing with celestial bodies where their values are on the reference table. There's also the value of g. G is also on the reference table as 6.67 times 10 to the negative 11 newtons meters squared over kilograms squared. Okay, now this is a very complicated set of units. It's really just there to help cancel out things so that you can get newtons in the end. That's all it is really. But anyway, this number, if you notice, times 10 to the negative 11, it's so small that when you multiply by this number, it makes the force very weak in comparison. That the only time it really makes any significant difference is when you have celestial bodies. So like the Earth, the Moon, the other planets, they have such large masses that the force of attraction between any two objects is so significant. Versus if you're just talking about two people sitting together right next to each other. Because this number is multiplying, it's such a little distance, but it's also smaller masses multiplied by a really small decimal. There's very little force of attraction really experienced between two people sitting next to each other because of this small decimal here. All right. Now, looking at some of these relationships here, greater masses exert stronger forces. So it's really about increasing the strength of the field, which then increases the forces between them. So again, these two bodies still experience the same forces between each other, but the strength of that force between them is all dependent on their combined masses multiplied together. And then shorter distances increase the force. So think about two magnets. When you pull them closer together, that small radius, you're dividing by a small number, it's going to make that force really big. But if you bring it further apart, you're weakening that force. So you don't feel that stronger force of attraction. So if you actually try to leave the Earth's orbit, you're going to feel less and less of the Earth's gravitational pull on you. So because we're right on the surface of the Earth, we feel that so strongly we fall back down to Earth when we jump up. But the further out you go, it has a weaker and weaker pull. And it's all based on the distance between the cores. Now, talking about gravity as a force, it's a force of attraction. So I know I talked about this in class. So again, we have two different masses. Their combined masses together are so huge, it causes such a huge force of attraction. But again, it's a force of attraction. So that means they exert forces on each other, and they're equal but opposite in direction. Now, the moon circles the Earth because it has a smaller mass. It's being pulled in by Earth's gravitational field. On the other hand, gravitational field lines are different. These are field lines. These are different from the forces that I drew in the other picture above. So these are the forces they exert on each other. They pull towards each other and such. Whereas this here shows the gravitational field, just the Earth alone without any other objects in play. So it's pulling things in. And now once it pulled something in, like the moon, they exert forces on each other like this. So because gravity is attractive, these force vectors will always be pointed towards each other because they are attracting each other. Okay? So again, by virtue of having mass, all objects in the universe, hence universal gravitation, exert forces of attraction towards each other just by having mass. So us included. Okay? And that is the end of this video. Take care, guys.